We're going to begin with some definitions and units. First, displacement, right? This is going to be delta x. This triangle right here is delta. It is a Greek letter. It means change. Generally, delta also means slope. So slope is a change in something. In this case, displacement is going to be the final minus the initial. You'll notice these subscripts right here. This little f means final, and this little I means initial. The unit for displacement, the traditional unit is going to be a meter. Of course, it could be anything like a kilometer, a centimeter. It could be an inch. It could be a mile. But we're not going to use any of those. We're going to stick to metric, and the traditional will be meter. If it's not meter, you might have to convert it. Next, velocity, delta v, right? The change in velocity is going to be delta x over delta t. Okay, this time, right? The unit for time is going to be in seconds. You'll notice I typed it up this way, but it should be really meter over second. Because in the numerator you have a meter, and in the denominator you have a second. The unit for velocity is going to be a meter over second. Acceleration is a change in velocity. So you'll notice that velocity was a change in displacement with respect to time. Acceleration is a change in velocity with respect to time. So it's almost like each one goes back to the previous one to define it. Acceleration is going to be the change in velocity over the change in time. Doing that, you know that velocity is a meter over second, and time is a second. So if we were to go ahead and do this, and then keep flip change, you would come to the conclusion that this is a meter per second squared. You are very well aware at this point that acceleration's units are meter per second squared. That is also the unit for gravity, which is a type of acceleration. There's an extra blank right here. We do have another formula for acceleration that may come in handy. Notice how it's delta v over delta t, but delta v by definition is delta x over delta t. So if I were to go ahead and replace that, right, acceleration is delta v over delta t. But instead of a delta v, I were to replace this with this fraction. If I do the keep flip change thing, I'm going to end up getting delta x over delta t squared. These deltas, right, these changes, delta is change. They require two points. You know, so there's always a final
Could you
initial.
say that again, please?
What if you don't have 2 points? What if you just have 1 point? Well, then you get instantaneous velocity. It's going to be x over t. Acceleration would be v over t. So it would just be the exact number, the exact value that I have at that moment. Motion graph. This is a displacement versus time. This is an x versus t. And it's very important that we are aware of the units. So consider for a moment that even though it's a displacement versus time graph, that if I take the slope, I would get meter over second, which is velocity. Let's look at some of these questions here. At exactly 3 seconds, how far did the bicyclist displace? So here we are at 3 seconds, right? At 0 seconds, the bicyclist hadn't moved yet. At 1, they had traveled this much. At 2, they had traveled this much. At 3, they had traveled this much. So at exactly 3 seconds, the bicyclist went ahead and had traveled 10 meters. How much did the bicyclist displace between 9 and 10 seconds? So we have to notice something here. If I'm going from each second that goes by, you'll notice that the bicyclist is displacing, right? They are leaving the starting point. So even at 4, I mean, they're not displacing as much, but they still are displacing. 5, 6, 7, 8, 9. Okay, now here we are at 9. Here's our initial. Here's our final. You'll notice that if we're looking only between 9 and 10 seconds, that for this displacement versus time graph, it actually doesn't have a slope, right? There is no slope. If we were to do the math, that's 15 minus 15 is 0. So whether you want to look at it geometrically based on the graph or mathematically, what actually happened between 9 and 10 seconds and this person was at rest. There was no movement. The average velocity, so we're going to go ahead and use these formulas, right? And look what's happening here. You're seeing all this fancy stuff, but really it's a slope. Remember, slope is y2 minus y1 over x2 minus x1. I'm proposing to you that velocity is x final minus x initial over t final minus t initial. It's the same thing. We just change the 2's to f's and the 1's to i's. There's a minus and there's a division. So from 0 to 3 seconds, that means that I'm going to start here and go to here with my time. right? There's your 3, here's your 0. On the x, the displacement, I'm going from 10 up here to 0 over here. Remember, you're breaking this apart. So you're looking at how, at the rise, right? How much did you rise? 10. With how much you ran? 3. With the second part, we're looking at 0 to 10 seconds, the entire thing. So we start here and we end here. What about all the points in between, Mr. Over? What about the various slopes? It doesn't matter because it's an average. It's an average. It's not an exact picture. It's an average. It's a summary of what happened during this time frame. So again, we look at this right here, 10 corresponds to 15 meters. At 0, it corresponds to 0. 10 seconds right here. And of course, the time was 0 originally. For your summary, what does the slope of a displacement versus time graph represent? Here's our next graph. Notice this no longer is displacement versus time. We will always, almost always, at least in this class, have time be the x-axis. But you'll notice that this time our y-axis changed. It became velocity. All right, so be careful with how to read this. Furthermore, you'll notice that this time there are positives and negatives. We generally will not have negative time because that would be time travel. All right, during what time intervals is this object traveling at a constant velocity? So on the previous graph, this region was a region of constant displacement, meaning that you weren't moving. You were stuck in one spot. So consider that anything that doesn't have a slope, where the slope would be 0, that would be a region of constant velocity. So notice from 0 to 0.75, here from 3 to 6, and here from 6 to 7. Those three regions have no slope. They have a slope of 0, and they are regions of constant velocity, which means everything else would be a change in velocity, a form of acceleration. So in this region from 0.75 to 2, there is actually what we call a deacceleration. It's slowing down. So imagine for a moment that we have a vehicle or a bicycle or a bird or something that's traveling at 1 meter per second. And now all of a sudden, by the time we hit 1, it's traveling at barely anything. And then all of a sudden it's doing negative. So this is a negative velocity we have here. It's deaccelerating. Okay, at some point though, it did hit a 0. Also, you'll notice that there is an acceleration, right? How do we know there's an acceleration or deacceleration? Because graphically, visually, if it doesn't flatline for a velocity time graph, it's going to go ahead and be a form of acceleration. So here is actually, it has a positive slope, and this would be acceleration, positive acceleration from 2 to 3 seconds. So between 3 and 6 seconds, I would have to go ahead and find the area of the shape. So what we have here is the area. In this case, would be the velocity times the time. I should do delta v times delta t. Remember, we want how much it displaced. Notice something interesting here, that if we had delta v is equal to delta x over delta t, if I want to get the x by itself, I'd multiply both sides by delta t. So what we're looking at is v final minus v initial times t final minus t initial. The final velocity is looking like 2. Down here in this shape, it's 0. T final is 6 seconds. T initial is 3 seconds. You'll notice that the seconds cancel out. You're left with the meter, 6 meters. Now, you didn't have to do all that, right? You could just simply have counted all these, right? Here's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And if you recognize your units, 6 meters, you're done. So don't forget how area plays a role. So notice something that with the velocity versus time graph, hint, left column idea, for a velocity versus time graph, the area is the displacement. Now the next question to you is going to be, what would the acceleration be? How do I find the acceleration? Remember, this is a velocity versus time graph. The funny thing about it is that it tells you the displacement and it can also tell you the acceleration, even though it's called velocity versus time. So let's look at the acceleration between 2 and 3 seconds from here to here. So from 2 to 3 seconds, right, we went ahead and set this up. We have 2 meters per second minus a negative because this was a negative 2. Okay, so remember the formula itself has a built-in minus, but in our problem, we also happen to have a negative 2. That gives you a positive 4. And then in the bottom, we have 3 seconds minus 2 seconds, that's 1 second. For a velocity versus time graph, If you want the displacement, find the area. If you want the acceleration, find the slope. At what instance is the velocity 0? Well, we got one right here at 1 second, one here at 2.5 seconds, and one right here at 7 seconds. We're going to return back to displacement versus time. No numbers this time. We have different regions. Recall, for example, when it flatlines, that means the displacement is constant. And then if there's a slope, then it's moving. So we know this would have a velocity between 2 and 3. And between 4 and 5, there would also be a velocity. But it's going downwards. This probably would be a negative velocity. Let's look at the questions. Between which two regions is the car traveling with a constant positive velocity? Oh, well, there you go. How do we know? Because it has a slope, and it has an upward slope. Remember, this is only true for displacement versus time. Velocity versus time is different. When is it traveling with a negative constant velocity? Well, again, straight line, right? Not a horizontal, but one with the slope. But this one is going downward. So between 4 and 5. Between which two regions is the card accelerating? Well, this is fascinating. So on a displacement versus time graph, if you end up having a curve, like a parabola or an exponential, then what you're looking at is acceleration. And of course, as we already noted, it's not moving between 3 and 4 because it is a horizontal slope, right? It's 0. It's a slope of 0. What does the slope of a displacement time graph represent? What does the area of a velocity time graph represent? What does the slope of a velocity time graph represent?
Great job, everybody!